Let's do a few examples of some Lewis structures. Lewis structures only pertain to covalently bonded compounds, in other words, molecular compounds. The way we tell that we have a molecular compound is that we've got a nonmetal and a nonmetal. Really, we could probably expand that to two things that are not metals, because metalloids would also count as not being metals, and they covalently bond or form molecular compounds. Let's go ahead and let's review the rules that I set out. Uh, First thing we would do is we would count the valence electrons available, and then we would draw a skeletal structure with the least electronegative atom in the center. That least electronegative atom is usually the singlet, the things that we have one of. Not always, but usually. You should still check for electronegativity. Or it's usually the one that's listed first. So you got three kind of clues, but always defer to the electronegativity as a clincher. Um, After we draw that skeletal structure, we'd connect to the center with the central atom with dashes. Then we would complete octets with dots. A couple of exceptions, or a few exceptions, are hydrogen. It would only get 2 electrons max ever. So really it never gets dots, because one dash is going to equal 2 dots and we're done. Beryllium, 4 electrons, satisfies its octet, so it doesn't go to a full 8, and boron only goes to 6 rather than 8. In these three, I can't really think of instances where we'd even give them dots. Let's put it that way. Um, Last but not least, we'd compare the electrons that we used to the electrons that we counted available in step 1. If we use too many, we'd erase some electrons, create some double and triple bonds to the central atom. If we use too few, we would check for the center to expand its octet. Anything in the third row or below on the periodic table can hold up to a maximum of 12 electrons. It doesn't have to go to 12, but it can if it needs to, because of D sublevel orbitals. There's room. Let's go ahead and do a few examples, and you'll see how this works. Our first example is nitrogen trifluoride. So the first thing we're going to do is count valence electrons. The way we'd do that is we'd go to the periodic table, and the periodic table is set up in groups 1, 2, 3, 4, 5, 6, 7, 8. Those group numbers tell us our number of valence electrons. Uh, Older periodic tables actually go 1, 2, 3, 4, 5, 6, 7. More modern periodic tables, you can see, go 1, 2, and then it's 13, 14, 15, 16, 17, 18. That last number, the 3, the 4, the 5, etc., still tells us the number of valence electrons available. So we've got nitrogen, which is going to have 5 valence electrons because it's in group 5, and then fluorine would have 7 valence electrons because it's in group 7. So let's go back, and we've got nitrogen, which is 5 valence electrons, plus 3 fluorines times 7 electrons each is going to give us a grand total of 26 valence electrons available. So what we would do next is draw a skeletal structure where we're going to put our least electronegative in the center, which is our nitrogen. So we've got nitrogen surrounded by 3 fluorines. What we would do next is we would connect to the center with dashes. So I'm going to make a dash between each of these outer atoms and our central. The next thing we would do is we would complete our octets with dots, exceptions being hydrogen, beryllium, boron. I do not have hydrogen, beryllium, or boron, so I'm going to go ahead and complete my octets. So this dash here counts as 2 electrons for fluorine, so I would give it 6 more electrons, or 6 more dots. Make those a little clearer. Same thing with this fluorine. Same thing with my last fluorine. Nitrogen has 2, 4, 6, so I give him 2 more. What I'm going to do is I'm going to count the electrons that I used. So I've got 6 dots on every fluorine, so that's 6, 12, 18, plus the 2 dots on nitrogen, that's 20, 22, 24, 26. If, I didn't mention this in the rules, but if the number of dots used is equal to the number of valence electrons that we set out as being available in step 1, then this is our Lewis structure. So this right here is our Lewis structure. That guy right there. That's our Lewis structure for nitrogen trifluoride. Let's go ahead and do a couple more examples here. Let's do H2CO. So my first step would be to count valence electrons. Hydrogen is in group 1, so I've got 2 times 1, plus carbon's in group 4, so that's another 4, plus oxygen is in group 6, so that's another 6, grand total of 12 electrons. Go over here, and we're going to put carbon in the center, since it's our least electronegative. Carbon, oh, by the way, hydrogen, since it only gets 2 electrons ever, it can never be a central atom. So of these 2 left, carbon is definitely the least electronegative. So I'm going to put an oxygen and 2 hydrogens around that. So there's my skeletal. I connect with some dashes, and then I complete octets. Hydrogen completes with 2 electrons. That is one of my exceptions, so it never gets dots. I'm not going to put dots on it because its 2 electrons are right here in this dash. So carbon, I've got 2, 4, 6, so I'm going to put 2 more on the carbon. I'm up to counting how many available versus how many used. I used 6 on the oxygen, another 2 is 8, 10, 12, 14 electrons used. However, I only had 12 electrons available. So that means what I need to do is create a double bond between the central atom and one of these atoms. Since hydrogen can only get 2 electrons, there's no, it'll never form a double bond or a multiple bond. So I've only got oxygen to choose from. What I do is I take 2 electrons off my, oops, 2 electrons off my central atom, I take 2 off of the oxygen, and then I add in a double bond. The net result is I pulled 4 electrons off, put 2 electrons back in that are now shared in this second covalent bond, and now I can recount my electrons used, and we've got 2, 4, 6, 8, 10, 12, 12 electrons used. This is my Lewis structure for this compound. Let's go ahead and take a look at another one here. We've got beryllium diiodide, and what we do is count up our valence electrons. I've got 1 beryllium, which is in group 2, I believe. Let's take a look here. Beryllium, yep, there it is, beryllium in group 2. So beryllium's in group 2. So I got 2 electrons there, plus 2 times 7, which is going to give us 14 plus 2 is 16 valence electrons available. I'm going to go ahead and draw a skeletal structure. I'll put beryllium in the middle. And then I've got an iodine on each side. And then I'm going to go ahead and put in my dashes, connect to the central, complete my octets. Beryllium, we said, was an exception. It's satisfied with 4 electrons, so he's going to get no dots. That's it. He's got 2 electrons here, 2 electrons here, grand total of 4 electrons. Beryllium set. So what I would do is fill in the octet for iodine. Each one of these has 2, 4, 6, 8. So I'm set, and what I'll do is count up my electrons used versus available. I used 2, 4, 6, 8, 10, 12, 14, 16 electrons used. So this is my Lewis structure for beryllium diiodide or beryllium iodide. Um, last example is xenon difluoride. So again, we're going to count up our valence electrons. I've got xenon, which is in group 8, plus 2 times 7, because fluorine's in group 7. That's a grand total of 14, 22 electrons available. Xenon, my least electronegative, is going to go in the center, flanked by a couple of fluorines. I'm going to go ahead and connect to the central with dashes, and then I'm going to complete octets. This will get another 6 dots. Brings these two guys to a grand total of 8. I'm going to put 2 more on xenon, or 4 more on xenon, and now I'm ready to go ahead and count up my valent, or my electrons used. I used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I only used 20 electrons. So I used too few. So what I said I would do is if I used too few, I would check for the central to expand. So I'm looking to see if I can put those 2 extra electrons that I need to use up, because I've got them available, on the central atom. I can do that if that central atom is in the 3rd row or below on the periodic table. Those guys can hold up to 12 electrons. Let's go ahead and go to the periodic table. Here's xenon way down here. Here's the third, oops, here's the 3rd row right here. So this is definitely below the 3rd row. So it contains d level orbitals, or d sublevel orbitals, so it can expand. So what I'm going to do is I'm just going to take those 2 extra electrons and I'm going to stick those on the xenon, and I'm set. I now have used 22 electrons, and I'm done. Really, if you just follow these steps, there it is, the extra electrons go there. 2, 4, 6, 8, 10, but he can go up to 12 because of those d sublevel orbitals. It's good. It's a good structure. So if you just follow these steps, should be no problem. I prefer this to the guess and check method that I learned when I was in high school. It's kind of foolproof. It's a pretty surefire way as long as you follow the steps. Surefire way to get a Lewis structure.